Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 1 of 3 on the topic of exploratory data analysis, and we'll discuss data types and summary statistics. Let's get started. When doing data analysis, the data we gather are a collection of characteristics about the things we study. We call those things variable because they change from observation to observation. Variables come in two flavors, categorical or qualitative, and numerical or quantitative. Qualitative variables are either nominal, which are observations recorded with a label or name, and ordinal, which is a category that implies some kind of ranking. For quantitative variables, there are discrete and continuous variables, which describe numerical variables and the values they can take on. Continuous variables are the most common that we encounter in hydrology. An example of a data type that employs all 4 variable types is a USGS flow measurement. These measurements record which agency performed the measurement, which is an unranked label and therefore a nominal variable. They also record the quality of the observation in a variable called measure rating. These have a ranking, with excellent being better than good and good being better than fair, and so on. These are ordinal variables. The duration of these measurements is measured to the nearest tenth of an hour, so a value of 0.15 hours can't be recorded. This makes the measure duration a discrete variable. Finally, the resulting streamflow measurement that was taken is a continuous value with a minimum at 0. An important distinction about numerical variables that is important to consider is whether the units of those variables is an interval measure or a ratio measure. An interval measure makes it so that values can only be compared by taking the difference between them, but the ratio between them is meaningless. An example of this is temperature on an interval scale, such as degrees Fahrenheit or Celsius. Contrast this with ratio measures, which can be compared both by difference and by ratio, and the value 0 has a meaning as none of this thing. Measuring distance in kilometers or miles is an example of a ratio scale. The ratio scale is stronger to use when evaluating data because of the concrete definition for 0. For temperature, if you wanted to work in a ratio scale, you would use an absolute temperature unit such as Kelvin or Rankine. For categorical data, we are still able to summarize these data in a numerical way, even if arithmetical operations aren't meaningful for the data. The summary statistic we use for categorical data is simply the count. The frequency table is one way to present this data, both by count and by relative frequency, which is the category's count divided by the total count. A chart that can be used to summarize categorical data is the Pareto chart, which is a display of the relative frequency of each category sorted in descending order from the most frequently occurring to the least frequent. Now we move on to numerical data summary statistics. Percentiles of the data give you an idea of the distribution of values within a sample. The alpha percentile of a data set is the value where alpha % of the data are below it. In Excel or R, it is easy to find the data corresponding to the desired percentile alpha. Both Excel and R interpolate their percentiles, so the percentile values do not always correspond to one of the data values. The 5-number summary looks at a subset of values that do a good job of summarizing the data set in a standard way. If someone says the 5-number summary, they always mean this grouping of values. The values from the smallest to largest are the sample minimum, the 25th percentile, the 50th percentile, the 75th percentile, and the sample maximum. The 25th percentile is also called the first quartile. The 50th percentile is the second quartile, or the sample median, and the 75th percentile is the third quartile. We will see in a coming discussion that other measures of a sample can be derived from the values in the 5-number summary. This will also come up again when we talk about linear regression, because it can be used to look at the model residuals, which is part of checking a regression model. Use of the 5-number summary is so common that in R, it is a built-in function that you can use on a dataset. Central tendency is important because samples tend to cluster around their central values, and it represents a reasonable value to expect of the sample. These first 3 measures we've seen before and are very common for summarizing data. The mean is the first moment of the sample. It is also the center of mass if you want to look at it in a physical way. The median is the point where 50% of the data are on either side. For symmetrical data, the mean and the median are the same value. The mode is the most frequently occurring value. For discrete data, this might be pretty simple to compute. You simply find the value that occurs the most often. For continuous data, it's a little bit harder. You might construct a histogram of the data and find the middle value of the tallest bar. You could also construct a kernel density plot and find the value corresponding to the tallest part of the density plot, like in this image. You could alternatively fit a parametric model, like a probability distribution, and get the distribution's mode. Data can have multiple local maxima, or be multimodal, but in general, we won't deal with data like that here. Typically, multimodal data arise in hydrology due to some amount of inhomogeneity, that is, the data were not actually sampled from the same population. Robust statistics are a way of summarizing or analyzing data that can be prone to outliers that have undue influence on estimating the properties of the sample. The sample mean can be sensitive to outliers. I always like to think of this example. What's the average income of a room containing you and 4 of your friends? Then, what happens to the average income when Bill Gates shows up? You could see how the mean value can be sensitive to extreme data points. Robust statistics try to find sample properties while being less sensitive to these kinds of unexpected data. The sample median has many robust properties and is useful in these situations as well. Here, I'll introduce 2 other measures that we use. The trimmed mean is a weighted average, where the weight is 0 for anything outside the window and 1 for anything inside the window. The 25% trimmed mean uses all values in the middle 50% to compute the mean. The 25% trimmed mean is also called the interquartile mean. You can adjust how much to trim off, but typical applications use 5 to 25%. In judged Olympic sports, sometimes a trimmed mean is used, where the maximum and minimum judged scores are dropped and the average of the remainder is retained. This has been called the Olympic mean before, and it's an effort to be less sensitive to outlier judges. Tukey's trimean is a weighted average of the quartiles with double the weight given to the median. It's a surprisingly good estimator for the central tendency of a dataset and can be derived from the 5-number summary. It is robust to outliers, but uses a little more information than just using the median, although the median does represent 50% of this estimate. I'm a big fan of this measure, and if I'm the reviewer for a report and you give me a trimean for a sample, I'm definitely going to give you a high five the next time I see you. Dispersion gives us a measure of how much the data in a sample spread out from its center. The variance and standard deviation should be familiar already, as they're the most common way to look at the dispersion of data. The variance is the average of the squared distance between each data point and the mean of the sample. The standard deviation is just the square root of the variance and has the same units as the data, where the variance has units of the data but squared. For the structural engineers, variance is conceptually similar to the moment of inertia of the data, where the axis is at the mean of the data, which is the center of mass. The chart on the right shows 2 samples that have a mean of 100, but the red density has a standard deviation of 10, and the blue density has a standard deviation of 50. You can see that larger values of a dispersion measure are associated with a bigger spread of the values in a sample, and less clustering around the mean of the sample. A statistic I use very frequently is the coefficient of variation, or CV. The CV is great for comparing things that don't have the same mean. This can come up when comparing measures from different unit systems, but both are ratio scales. It can be finicky, though, when the mean gets close to 0. Means close to 0 can happen when the data are on an interval scale and not a ratio scale, or if the overall magnitude of the data is very small, so be careful in those cases. It also isn't very useful if the mean is negative. In some applications, the reciprocal of the CV is called the signal-to-noise ratio. Here are some robust measures of dispersion. They tend to be less sensitive to outliers, which can inflate dispersion measures more than central tendency measures. The interquartile range, or IQR, is the most common robust dispersion statistic. It is simply the 3rd quartile value minus the 1st quartile value. It tells you how wide the middle 50% of the data are. It is very easy to compute from the 5-number summary. This metric gets a lot of traction in the social sciences and is frequently encountered in academic literature. If you take the IQR and divide it by the sum of the 3rd and 1st quartile, you get the quartile coefficient of dispersion. I don't see it used as often, but it's attractive. Dividing by the quartile values makes this measure scale invariant like the coefficient of variation. This last measure is probably the least used of these 3 because it takes the most work to compute. For each value in your dataset, find the absolute distance between it and the median value. Then for all of those absolute distances, find the median one. That finds the median absolute deviation, which is the median distance between each data point and the median of the sample. It's quite robust to outliers, but does take a bit of extra work to compute. Asymmetry measures describe if values tend to occur on the high end or the low end of the sample more often than in the other end. Symmetrical data usually have an asymmetry measure close to 0. If large values are more common than small values, the data have a positive asymmetry, sometimes called a right skew. In the opposite case, when small values are more common than large values, the data have a negative asymmetry, sometimes called left skew. Asymmetry measures are unitless. The moment-space measure of asymmetry is the coefficient of skewness. There are a few ways to compute the product skewness, but this is the most commonly used, and it's the method in Bulletin 17 computations. The fanciness with the n terms at the start is a degrees of freedom correction that tends to 1 over n as n approaches infinity. The coefficient of skewness is a central moment. It is also a standardized moment. By dividing by the cube of the standard deviation, it's made unitless. Yule's coefficient is a quartile-based measure that can be derived from the 5-number summary. It makes a lot of sense when you look at the unsimplified version. If the midpoint of Q3 and Q1 is less than the median, the coefficient is negative. If this midpoint is positive, then the coefficient is positive. In this video, we discuss data types and summary statistics. 3 key points to take away from this video are: data can be recorded in 4 ways, as nominal, ordinal, discrete, or continuous variables. The data summaries you generate are dependent on the kind of variable that you've observed. And last, robust statistics are a method for describing a dataset in a way that tends to be resilient to outliers. Thanks, and tune into the next video in this series on exploratory data analysis to learn about data visualization.